So firstly, the aluminium adjuvants. I would like to talk a little bit about them since they are such a long-term running workhorses in the field of vaccination. A reason why they are not ideal is because they do induce a Th2 response rather than a Th1 response, but the combination with other TLR ligands can partly inhibit this Th2. So what are the aluminium adjuvants? The first is the old one that we call Alum, and in order to make this adjuvant, you need to precipitate crystals of the alum potassium sulfate together with the antigen, and this precipitation actually does not give very reproducible results. The resulting vaccine can be quite variable, and therefore the alum is absorption of antigens to preformed aluminium gels, and these aluminium gels can be either aluminium hydroxide, referred to as AH, or aluminium phosphate adjuvant. So the hydroxide has a positive charge on it at neutral pH, and you must inject this at neutral pH. This means that it may be more beneficial for antigens which are negatively charged, which have their isoelectric point at like the negative part. It is a crystalline adjuvant, and the crystals are long and needle shaped, and the brand names here are Al-Hydrogen and Re-Hydralgel. These two adjuvants are still used in vaccine development. So also aluminium phosphate is a useful version of the aluminium adjuvants. It has a negative surface charge at neutral pH, which then is beneficial for positively charged antigens. It's not crystalline. The fact that it's not crystalline makes it actually more easy to work with, since the types of crystals will make the adjuvant to have different properties in the absorption of the antigen. So very small crystals would absorb much more antigen, while larger crystals would absorb less antigen, and crystal formation is quite hard to control. So what are the mechanisms behind the function of the alum or the aluminium adjuvants? So the first is that it makes the antigen particulate. So it turns it into either small crystals or small aggregates. These particles are much easier for the phagocytic antigen presenting cells to take up, since there are more processes that involve engulfing larger particles rather than just sampling the environment for soluble antigens. So it's a matter of antigen concentration. It also helps to target the antigen to antigen presenting cells, while once the antigen is bound to the adjuvant, it's fairly stable. And it's not just fairly stable, it's kind of tightly bound to the alum particles, and this also changes the property and the folding of the proteins, because they want to maximize their surface that they face towards the alum particle. So this may be disruptive and destroy the antigen epitopes, which we've talked about before. Anyway, the third point here is that the alum retains the antigen at the injection site, which helps to cause and maintain a local inflammatory reaction. This has been referred to as a depot effect, but once investigated properly, it turns out that this depot effect is actually not necessary for the function of the aluminium adjuvants, and there are aluminium adjuvants that are cleared very quickly, and depending on the route of infection, for example IP infection, it's rapidly clearing the alum complexes, and they still work. There has also been shown that some aluminium adjuvants seem to be able to activate the NLRP3 inflammasome. I'm not putting that into the slide, I just want to mention it, because it turns out that if you delete the NLRP3 pathway in mice, the adjuvant works just as well. So even if it does activate the NLRP3 inflammasome, it doesn't seem like the mechanism of action for the aluminium adjuvants is relying on the NLRP3 inflammasome. So now I would like to mention also the oil in water emulsions, because they also have a very long history in vaccine research. At the moment, the oil in water emulsion that is used in human is called MF59, and it's based on a molecule called squalene, which oily molecule found in plants and humans and a bit of everywhere. It's nothing special. This is emulsified using detergents, so tween, and then it's mixed inside of this emulsion. There is a mixture of the antigen, or what do they call here, the drug substance. The MF59 has been used in a flu vaccine for old persons, and in Europe it has been used quite a long time. So this is an interesting concept, that an emulsification itself has an adjuvant effect, even if the components of the emulsion does not have in themselves adjuvant properties. The other very important adjuvants that use this emulsified adjuvant effect is the incomplete Freund's adjuvant, the IFA. And here the adjuvant is paraffin oil and surfactant, which create the emulsion. And before the incomplete Freund's adjuvant, we often use the complete Freund's adjuvant, which in addition to the paraffin oil and the surfactant contains heat-killed mycobacteria. So tuberculosis or some other form of mycobacteria added into the mixture. So when the incomplete or the complete Freund's adjuvant is mixed with an aqueous solution of antigen, the adjuvant forms this really viscous water in oil emulsion. And here the antigens are also trapped in the water phase. As an experimental adjuvant, the CFA has a very long history, and the active component of the CFA is called myramyl dipeptide, and this molecule itself can replace the dead mycobacterium, and the myramyl dipeptide will activate NOD2 intracellular inside of the cells, and the TLR2. And the complete Freund's adjuvant is used as an emulsion on the skin or intradermal injections on animals, and it causes terrible lesions, and it's toxic. Both these two adjuvants cause autoimmune responses, and it's a way for inducing different types of rheumatoid arthritis. So they are not ever used in humans, but they were very useful for making antibodies in the early days. Now we're going to move forward to the mycobacterium, because it's very relevant today.
One of the early important vaccine was the vaccine against tuberculosis. So, the original vaccine was an attenuated Mycobacterium bovis bacillus, and this was isolated by two guys called Calmette and Guerin. This cultured strain was kept for many years before it was properly conserved, and it was attenuated by passaging it in culture. They eventually did preserve a reference strain by lyophilization, which is the process of drying bacterial spores in vacuum, and they keep for a long time. However, before they did this, they sent out the strain, the vaccine strain, to several different cities around the world. So therefore we have now BCG Russia, BCG Japan, and BCG Copenhagen. and they are all from different passages from this original strain. The vaccine is inoculated in the upper arm, as you can see in the middle picture, and resident dendritic cells that sit in the skin or the layers just below the epidermis, they will take up the bacteria, the living bacteria, and travel to the lymph node where they activate the CD4 T cells, and they induce a type 1 polarizing immune response with the cytokines such as IL-12, IL-18 and interferon gamma secreting T cells. And it therefore is a very canonical immune response that we receive from the BCG vaccination. The BCG vaccination is a very strong immune activator, and it also activates something called trained immunity. Trained immunity is the enhanced ability of macrophages to produce cytokines such as TNF-alpha and IL-6 in response to an unrelated microorganism and to react via TLR to other pathogens. A response in these macrophages which is primed by the BCG vaccination but not antigen specific. This trained immunity is mediated by the NOD2 receptor signaling, and it involves epigenetic modifications of these macrophages. Natural killer cells have also been demonstrated to contribute to the trained innate effect, both in humans and mice, to the BCG vaccine. Innate immune cells, they alter their metabolism and they switch from oxidative phosphorylation to aerobic glycolysis once they will encounter new pathogens. So trained immunity is reduced if monocytes from controls are stimulated with irradiated BCG bacilli rather than live bacilli. This is due to the ability of the live bacillus to escape the endosome once it's taken up by macrophages or dendritic cells and enter into the cytoplasm. It is in the cytoplasm where it will encounter NOD2, which then mediates this trained immunity effect. Irradiated BCG will be trapped in the endosome and doesn't have the active function of transitioning into the cytoplasm.